Work and kinetic energy. Work, the energy of an object changes if an exchange of energy occurs between the object and its environment. Such a transfer can occur due to a force or due to an exchange of heat. We discussed the exchange of heat in other chapter. Here, we discuss the transfer of energy via force, a process known as doing work. Work W is the energy transferred to or from an object by means of a force acting on the object. Energy transfer to the object is positive work, and energy transfer from the object is negative work. Work then is transfer energy. Doing work is the act of transferring the energy. Work has the same unit as energy and is a scalar quantity. The term transfer can be misleading. It does not mean that anything material flows into or out of the object. Work and kinetic energy. Let's now relate the work done on an object by a force and the corresponding change in the kinetic energy of the object. If the force changes the speed of the object, it also changes the kinetic energy of the object. Work done by a single constant force. Single force, constant force. We look at the situation. A bead is moving along x-axis with displacement d. Under force, this force is single, constant. Constant means during the motion, its direction and its magnitude does not change. Phi is the angle between F and X. This must be a constant acceleration. So we have this formula v squared equals v0 squared plus 2ad, where a is acceleration along x direction. We multiply 1.5 on both sides. We have this new look at it. And here we see half and 2 cancel out. max, which is the fx. This is the component of forces on x-axis. We rewrite this equation as K final equal to K initial equal to F to D. Half mv squared is the kinetic energy at the final state. Half mv squared is initial kinetic energy, and this is the work done by the force. If the kinetic energy is the only types of energy of the object being changed by the force, then the change delta K in kinetic energy is equal to the work done by the force. Delta K, K final minus K initial equal to W. Or K final is equal to K initial plus work done by the force W. Work-Kinetic energy theorem. Half mv final square minus half mv initial square equals F dot D, the work done by the force. This is the dot product by two vectors. So by definition, it is equal to F D cosine phi, where phi is the angle between these two vectors. So we rewrite it with the df cosine phi. This is the component of F along the displacement of D. To calculate the work done on an object by the force during a displacement, we use only the force component along the object's displacement, F cosine phi. The force component perpendicular to the displacement does zero work. Work done by a constant force can be rewritten as this. F equals F dot D. The dot product equal to FD and the cosine phi, where phi is the angle between the directions of the displacement D and the force F. W equal F dot D equals FD cosine phi. If F is in the same direction as D, so phi is smaller than 90 degrees, cosine phi is positive. It's positive work. If F is opposite the direction of D, they are opposite direction. The phi is between 90 degrees to 180 is a negative number, so the work done is negative. A force does positive work when it has a vector component in the same direction as the displacement, and it does negative work when it has a vector component in the opposite direction. It does zero work when it has no such vector component. In other words, phi is 90 degrees. Net work done by several forces. When two or more forces act on an object, the net work done on the object is the sum of the works done by the individual forces. For example, we have many forces. The net force sigma I, Fi, is equal to F1 plus F2 plus F3 and so on. The work done by these forces is equal to net force dot D. We put this sigma Fi in, we get F1 dot D plus F2 dot D plus F3 dot D, and so on. And F1 dot D is the work done by F1. F2 dot D is the work done by F2, and so on. Work-kinetic energy theorem. Delta K equals K final minus K initial equals work done by the force. Rewrite it: half mv final square minus half mv initial square equals sigma Fi dot D. If the object's energy other than kinetic energy is being changed by the force, then above equation do not apply. A kinetic frictional force, for example, can change both the kinetic energy and the thermal energy of an object. In that case, they do not apply. Thermal energy is associated with the random motions of atoms and molecules within an object. Sample. Figure A shows two industrial spies sliding an initial stationary 205 kilogram floor safe, a displacement D of 8.50, straight toward their truck. The push F1 of spy 001 is 12.0 Newton, direct at an angle 30 degrees downward from the horizontal. The pull F2 of spy 002 is 10.0 Newton, direct at 40 degrees above the horizontal. The magnitudes and the directions of these forces do not change as the safe moves, and the floor and safe makes frictionless contact. A. What is the net work done on the safe by forces F1 and F2 during the displacement D? We look at free body diagram of the safe. Four forces acting on it: normal force from the floor, gravitational from the earth, push F1 from the spy 001, and pull F2 from spy 002. The result, it moves along the direction with displacement D. The work done, let's do F1. F1 is F1 dot D equals F1D cosine phi 1, Here, phi 1 is the angle 30 degrees. They are positive. This is F2, W2. W2 is F2 cosine phi 2 is the component of F2 along the displacements. Okay, so this is what the net work done on the say 4K you put together. We take three significant figures as given. So it's 153 joule. Question 2. B. During the displacement, what is the work Wg done on the saved by the gravitational force Fg? And what is the work Wn done on the saved by the normal force N from the floor? By definition, the direction between the gravitational force downward and the displacement horizontal is 90 degrees. So this work done is 0. Also true for the normal force, because the angle between the normal force upward and the horizontal is 90 degrees. So this is 0. Question C. The safe is initially stationary. What is its speed, V final, at the end of the 8.50 meter displacement? So we have the work then is equal to the kinetic energy change. We put this number in, we get a set. Vi is 0 initially, so we get this number easily. Okay, W2 over m square root. Sample. During a storm, a crate of cream is sliding across a slick, oily parking lot through a displacement d equals minus 3.0 I. While a standing wind pushed against the crate with force F equals 2.0 I minus 6.0 J. The situation and the coordinates exist as shown in the figure. These coordinates. Question A. How much work does this force from the wind do on the crate during the displacement? By definition, W equals F dot D. F is 2.0 I minus 6.0 J. D is minus 3.0 I. So Ij is a constant. So we do this one, rewrite this one. 2.0 minus 3.0 dot I dot I. Minus 6.0 minus 3.0 J dot I. We know I dot I is 1.1 cosine 0 is 1. J dot I, they perpendicular, equal to 1.1 cosine 90 degrees is 0. So this term is 0 because J dot I is 0. So we get this I dot I equal 1. We get minus 60. Question B. If the crate has a kinetic energy of 10 joule at the beginning of displacement D, what is its kinetic energy at the end of D? It's very simple. K final equals to Ki plus W. That equals 4.0 joule. In this case, because kinetic energy is the only change of energy, so we can use this theory.